today. My tomorrow must be greater than today.
His hand cannot short, that it cannot reach to you. His eyes in the blind, he cannot see your teeth. His ear.
Good afternoon, students. You are welcome to today's class. We are going to continue with the topic we discussed last week. That is heat energy measurement. But before we go into today's topic, we are going to summarize the topic we treated last week. If you can remember, last week we treated heat energy measurements. Under it, we discussed some subtopics like specific heat capacity. Alright? So we discussed different methods that can be used to measure specific heat capacity, like the method of mixtures and electrical method. So specific heat capacity can be calculated using any of these methods. Alright? So but today I will summarize it before we go into our new topic. Specific heat capacity can be calculated using the method of mixtures. And generally, the formula that can be used to calculate specific heat capacity is given as H M times C times theta, where H stands for quantity of heat, M stands for mass of the substance, C stands for specific heat capacity, and theta stands for temperature change. In the sense that theta is given as theta 2 minus theta 1, where theta 1 is the initial temperature and theta 2 is the final temperature after supplying heat to the substance. So if you want to get temperature change, you will just find the difference between the two temperatures. That is theta 2 minus theta 1. So from here now, let's call this equation 1. We can make C, which is specific heat capacity, the subject of the formula, and we get the equation C is equal to H over M2. So we can use this second equation to find the specific heat capacity of the substance. Is that clear? So we said the two methods that can be used to measure specific heat capacity is either by method of mixtures or by electrical method. By the method of mixtures, two different substances at different temperatures are mixed together. Alright? Assuming you want to take your bath with warm water, what will you do? You first of all boil hot water and mix it with cold water. Mix the two until you get your desired temperature. Right? So, what actually happened there is that the hot water will lose heat. It will give out heat. And the heat given out will be absorbed by the cold water. Therefore, last week we established the fact that heat lost by the hot substances is equal to heat gained by the cold substances under method of mixtures. Is that understood? And we also learned about the electrical method of measuring specific heat capacity. In the electrical method, we found out that, assuming, okay, let me give you this illustration. Assuming you want to use your electric heater or your boiler to heat water, to boil water, what will you do? You will plug the boiler to the socket and it will begin to supply electrical energy. So the electrical energy supplied by the boiler is used in heating the water. Is that clear? So that means that the heat energy supplied by the electrical energy is equal to the heat energy absorbed. That is, the electrical energy supplied by the boiler or the electric heater is equal to the heat energy absorbed by the substance. So we say that to mc theta, that is, heat energy supplied by the appliance is equal to quantity of heat absorbed by the substance. Is that understood? Where I stands for the current, V stands for the potential difference, T is the time duration of boiling the substance. Then M is the mass of the substance measured in kg, and C is what? The specific heat capacity, and theta, the temperature change. That we can use this equation to calculate specific heat capacity, right? Then, you know, in physics, unit is very, very important. So we can't just express specific heat capacity without telling you the unit of measurement. So how do we derive the unit of measurement? Heat is measured in what? Joules. Mass is measured in what? Kg. And temperature is measured in either degrees Celsius or Kelvin. Alright? Therefore, the unit of measurement of specific heat capacity is what? Joules per kg per Kelvin, or per degree Celsius. Is that okay? So let's now come back to this. We say that electrical energy supplied is equal to quantity of heat obtained. Alright? That is using electrical method of measurement. Is that clear? So this is just the summary of what we did last week. Now, let's start with the definition of latent heat. What is latent heat? Latent heat can be defined as the heat supplied or removed which causes a change of state without a change in temperature. Let's look at definition of latent heat of fusion. The latent heat of fusion can be defined as the quantity of heat required to convert a substance from its solid to its liquid state without a change in temperature. Let's look at the definition of specific latent heat of fusion. Specific latent heat of fusion of a substance is the quantity of heat required to convert a unit mass of the solid at the melting point to its liquid form without a change of temperature. Now that we have understood these definitions, let's now go into the calculations. Example 1. How much heat is required to change 3 kg of ice at 0 degrees Celsius to water at the same temperature? Given that the specific latent heat of fusion of ice is 336,000 joules per kg. How to solve it? Now, in the question, remember we are given the mass of ice as 3 kg and the specific latent heat of fusion of ice as 336,000 joules per kg. Is that okay? Now, how do we find the quantity of heat required in melting the ice? From this, we now apply the formula which is giving us H is equal to, alright, where H is the quantity of heat required, M is the mass of the ice, which is 3, okay? And L is the specific latent heat of fusion of ice, which is given in the question also. Now we say 3 times 306,000. What will they give us? So the quantity of heat required in melting the ice is giving us 10.08 times 10 raised to power 5 joules. we solve another. Let's look at the second example. A calorimeter contains 600 grams of water and 100 grams of ice at 0 degrees Celsius. A piece of hot metal of mass 1 kg is gently added to the mixture in the calorimeter, and this causes all the ice just to melt. Calculate the initial temperature of the metal, given that the specific heat capacity of water is equal to 4.2 times 1000 joules per kg per degree Celsius. Specific heat capacity of metal equals 4.2 times 10 raised to power minus 2 joules per kg per degree Celsius. Given also specific latent heat of fusion of ice is equal to 3.36 times 10 raised to power 5 joules per kg per degree Celsius. Solution. In the question, we are given the mass of water as 600 grams, but you have to change the unit to SI, unit of measurement. That is by dividing 600 by 1000, because 1000 grams will give you 1 kg. So 600 divided by 1000 will give you 0.6 kg. Is that understood? The mass of ice is giving us 100 grams. When you change it to kg, you get 0.1 kg. Initial temperature of ice and water is 0 degrees Celsius. Then mass of metal is given in the question as 1 kg. Initial temperature of metal, we don't know it. So let's assume it is T degrees Celsius. We are asked to calculate it. The specific heat capacity of water is given in the question as 4.2 times 10 raised to power 3 joules per kg per degree Celsius. Then, specific heat capacity of metal is also given in the question as 4.2 times 10 raised to power 2 joules per kg per degree Celsius. Also, the specific latent heat of fusion of ice is also given as 3.36 times 10 raised to the power 5 joules per kg per degree Celsius. We have to find the initial temperature of the metal. The ice and the water is the content of the calorimeter. Okay? And after that, the hot metal was added and everything mixed together until the final temperature of the mixture is obtained. Okay? Now, the final temperature of the, we are asked to find the initial temperature of the metal. Now, we have ice and water at 0 degrees Celsius. Remember, the 0 degrees Celsius is the melting point of pure ice at standard atmospheric pressure of 760 millimeters mercury. Is that clear? Now, when the hot metal was added, the temperature did not increase, so it remained at that stable temperature of 0 degrees Celsius. So that means that the hot metal gave out heat, and the heat was absorbed by the water and the ice content. Is that clear? So the heat, since there was no increase in temperature, that means that the heat was just used for is used in melting the ice. That means that heat is what? The latent heat. So we have to find that latent heat of melting ice, which is giving us H is equal to mn. Is that okay? Which is mass of ice 0.1 times, and the specific latent heat of fusion of ice is giving us 3.36 times 10 raised to power 5. Is that clear? So this is the quantity of heat absorbed. The quantity of heat absorbed. Let's now find out the quantity of heat given out by the hot metal. The quantity of heat given out by the hot metal is given as mc theta. Remember, this is the initial temperature of the metal, and the final temperature of the mixture is 0 degrees Celsius. Is that okay? Now, the mass of the mass of the metal is 1 kg, and the specific heat capacity of metal is given as 4.2 times 10 raised to power minus 2 times the temperature change. That is the initial temperature, the final temperature of the metal minus the initial temperature. So this is the initial temperature. And remember, the initial temperature of the metal will now be greater than the final temperature of the mixture. Are you getting it? Because the metal lost some heat to the mixture. So that means the initial temperature is now T, which we don't know, minus the final temperature of the mixture, which is 0 degrees Celsius. Is that okay? Now, that means, according to the fact established in method of mixtures, heat lost by hot substances is equal to heat gained by cold substances. That means we now say heat lost by the hot metal, which is 1 times 4.2 times 10 to the power minus 2 times bracket T minus 0. This is the heat lost by the hot metal, which is equal to heat gained by the ice, content of ice and water, which is 0.1 times 3.36 times 10 raised to the power 5. Remember, the water did not gain any heat because the temperature remains steady at 0 degrees Celsius. It's only ice that absorbs that heat that it is used in melting, in change of state. Is that clear? So for this, and T minus 0 is still T. So we have 1 times 4.2 times 10 to the power minus 2 T is equal to 0.1 times 3.36 times 10 raised to the power 5. If we make T the surface of the formula, we have T is equal to 0.1 times 3.36 times 10 raised to the power 5 all over 1 times 4.2 times 10 raised to the power minus 2. So use your calculator to evaluate this. You get 80 degrees Celsius. Therefore, this is the initial temperature of the metal. Is that clear? We will now come to the end of the calculation. But as I normally tell you, these few questions that I solved is just to show you how to solve questions on this. Go to YF past questions, you will see many questions, even in your textbooks, in the exercises. Try to solve more. If you try to solve any of them, if you can't solve them, or if you encounter problems during solving, call me and ask me questions. I will help you. So thank you very much. We will stop here. Next time we will continue with the topic. We've not finished the topic.